What's up, everybody? We're back for another lesson, and today we're going to be working with indirect measurements. So we're going to be taking everything we've learned with similar triangles and all these theorems to set up proportions, and we're going to use it in some word problems and kind of in like a real world type of situation. So to start off, we're just going to practice. So if we have two pairs of similar triangles, right? We have one problem on the left, one problem on the right. Let's get started. And what we could do is we could match up the corresponding parts, right? So if I look, I could say 6x are going to be corresponding, which means they're in the same place of each triangle. Then 4, 3 are corresponding. So then we could set up a proportion using this information. What I'm going to do is my left triangle over my right triangle. So we're going to put 6 over x equals 4 over 3. And when we do this, we then just, as we've been doing, and we should all be masters at now, cross multiply. So we get 4 times x will give me 4x equals 6 times 3 will give me 18. And then last but not least, we get out our trusty dusty calculator and we divide by 4 on both sides. We're left with x equals what? Pull out my calculator. Get 18 divided by 4. That's going to give me 4.5. And then we do the same thing for our second one. Once again, I'm going to just underline the corresponding parts. We're going to have 9, 7 are corresponding, and then 15x. Once again, we just set it up. We get 9 over, I don't like the way that 9 looks, 9 over 7 equals 15 over x. Now, notice the numbers from the same triangle are both up top, and then numbers from the same triangle are both down below, right? They're like buddies. They come from the same area, so they stay together. Something to keep in mind. And then we cross multiply once again. We do 9 times x, get 9x equals, and then we have 7 times 15 to get, I don't know, 105, I think it's going to be, but let's just double check. So, yeah, 105. 5. And then once again, all we have to do here is we divide by 9 to get rid of that number next to my variable. And we're left with x equals, plug it into the calculator, we get 11.6, we're going to round to 0.67. So remember, we're rounding to our 100th place there. The second decimal is our 100th place. Awesome. So that's just a little review of our setting up similar triangles and proportions within them. So today's lesson is called Run It Up the Flagpole. And as I said, we're going to be doing applications of similar triangles. So taking the knowledge that we learned, we're going to be applying it to word problems and real life scenarios. So today we're going to identify similar triangles to calculate indirect measurements. And we're also going to use similarity to solve for unknown measurements. So let's look at our first problem. It says Maureen goes to the park and uses the mirror method to gather enough information to calculate the height of one of the trees. So just to clarify for you guys, the mirror method is if you take a mirror and you put a dot in the middle of it, and you put it on the ground, you back up and you look at the mirror and you back up so that the dot is now reflecting the top of the tree. So the tree, you'll see the tree's reflection in the mirror, and the top of the tree is right where the dot is, then you know that these proportional triangles are being set up. A lot of work behind it, a lot of things, but it basically, you're able to figure it out due to the angles that goes on there too. But it sets up similar triangles like we have here. So the figure shows the measurements, and we want to calculate the height of the tree. So first things first is always when we have word problems like this, figure out what it's asking you for. It's asking us for, it says calculate the height of the tree. So the height of the tree is going to be our variable. So here we're going to put an x, right? Because that's the height of the tree. So now we need two pieces of information for each triangle. On my left triangle, our height is 5.5. Down here we have 4, as we see by these markers. But we don't know what this chunk is here because the whole chunk is 16. We have to do some scratch work. I'm going to say 16 minus 4. That's going to give me 12. So this chunk here is 12. And now we could set up our proportion, just like we did in the do now. Basically, same situation, right? Just have to figure out what the corresponding parts are. So we're going to say, I'm going to take my bigger and put it over the smaller. So we're going to say x over 5.5. So that's the height of the tree over the height of our person equals, or height of Maureen. She has a name. And then we're going to do the distance from the mirror to the tree, 12, over the distance from the mirror to Maureen, 4. And now we just cross multiply and solve, just like we've been doing. So x times 4 gives me 4x. Equals. And then we do 5.5 times 12. We just get a calculator to make quick work. 12 times 5.5 gives me 66. So then, once again, now we're at that one-step equation. We just divide by 4 on both sides. It cancels, and we're left with x equals 16.5. So what? Now we just need to write this as our answer. We could say the height of the tree is 16.5 feet. Boom. There's our answer. The height of the tree is 16.5 feet. It was good to write your answer out like that so you can demonstrate to whoever is looking at it that you understand what it's actually asking you, not just how to move the numbers around. Cool. Next up, we have another word problem, a little bit of a different situation, but it's gonna come out to be kind of the same. So it says Stacy notices that another tree casts a shadow and suggests using the shadows to calculate the height of the tree. She lines herself up with the tree's shadow so that the tip of her shadow and the tip of the tree's shadow meet. She then measures the distance from herself to the tip of the shadows, and then measures the distance from herself to the tree. A diagram of the situation is shown. Calculate the height of the tree. Explain your reasoning. So, once again, what can we do here? What we could do here is we could set up similar triangles again, right? Right here, we could set up similar triangles. We know they're similar because we have the right angle. So that's angle. These two right angles are congruent. And then both of them share this angle here. If they share that angle there, we could say that we have angle-angle similarity if we think about our triangle congruency shortcuts or triangle similarity shortcuts. But now we just need to set up our problem. For the small triangle here, we have our height is 5.5. The height of the tree is what we're looking for. So once again, calculate the height of the tree. That's where we put our variable in. I'm going to throw an x here, right? The height of the tree is what we want to know. We have our base of our small triangle. but we don't necessarily know the base of the big triangle. We have to add again. We're going to say 15 plus 6 equals 21. So now we know that this whole thing is 21. Now we could set up our proportion, right? So we're going to do, we go height over height. So height of the tree, x, over height of our person, 5.5. And then we're going to do, remember, since this is height of the tree, we have to do base of the tree up top. So 21 over base of our person's shadow, right, is 6. And once again, cross multiply and solve. So let's cross multiply. We go x times 6. And that's going to give me 6x. And then we're going to do, put that equal sign in there. And we're going to say 5.5 times 21. Once again, get that trusty dusty calculator out. 21 times 5.5. It gives me 115.5. 115.5. And now we just have to divide both sides by 6. And we get x, well, on my left side it cancels, so we're left with x equals 19 point, oh, I wrote it too. 19.25. So once again, just write out your answer. So we could box this off, but let's write out the answer. The height of 3, that's F, 3 is 19.25 feet. The height of the tree is 19.25 feet. Period. There we go. Wrote out an answer. Once again, use similar triangles to solve a word problem. This is something you can actually do in real life, right? If there's a shadow of a tree with your shadow, you can technically do this and figure out these problems. Next up, it says Emma spikes a volleyball, so it bounces off the ground 4 feet away from her. Her hand was 5 feet off the ground to hit the ball. The net is 6 feet beyond the position where the ball hit the ground. The ball bounced over the net, just grazing the top of it. How high was the net? Now, here's the thing. We have a diagram and there's some things labeled, like points, like Emma's hand, where the ball hits the ground, and the top of the net, but we don't have any of our numbers filled in. So for this problem, we actually have to go and fill in our numbers. So let's go do that. So first one, let's reread through this. It says her hand was 5 feet off the ground. So we have to figure out where's Emma's hand, where's the ground. So this distance here is going to be 5 feet. Next up, it says, and the net is 6 feet beyond the position of where the ball hit the ground. Oh, sorry. We missed a number. I missed one. Sorry. So Emma spikes the volleyball so it bounces off the ground 4 feet away from her. So this distance here will be 4 feet. And now we could go back and we could say, and the net is 6 feet beyond the position where the ball bounces. So the ball hits the ground here. The net is 6 feet away from that. So this is going to be a 6. And we want to know, what do we want to know? How high is the top of the net? So this here will be our x. Now we can set up our proportions. We have similar triangles again. So let's set up our proportions. So in order to do that, we have corresponding parts. I'm going to take Emma's height, or her hand height, 5. And we're going to put that over the height of the net, x, equals Emma's distance away from where the ball hit, 4, to the distance of the net from where the ball hit, 6. And as we've been doing, you may guess, cross multiply. X times 4, get 4x, equals, and then 5 times 6, give me 30. Last but not least, and like we've been doing, we divide by the number next to my x. We get rid of it, 4 on both sides. And that's going to give me, just do 30 divided by 4. It's going to be 7.5. We get x equals 7.5. So now we have to ask ourselves, what does that 7.5 mean in this context? So what it means is the net is 7.5 feet tall. Boom. And we answered our question. We answered our question. You're just using the same situations. We just answer the questions that are technically real life scenarios. So guys, as I always say, if you have been confused by any of these problems so far, please reach out to your teacher, whether it's me, whether it's Miss Harris, whether it's another teacher that I might not know. But if you are confused, make sure you ask for help, have someone re-explain it, or leave a comment down below and ask a question, and I will do my best to get back to it. But let's keep it cruising. We're not done yet. So now we're doing some more determining with indirectly. So let's look at some more examples. Here. First one, it says a group of friends are visiting a park. Lauren stands on one side of the creek. Caleb stands on the other, or stands directly across the creek in the figure shown. So let's see what we got going on here in our figure. So Lauren's here. Caleb's here, right? So it says Caleb is standing 5 feet from the creek. So this distance is 5 feet. And Lauren is standing 5 feet away from the creek on the opposite side, right? Each friend walks away from the other in opposite direction. Caleb walks 50 feet. Lauren walks 12. What we want to know is what, though? Because this is just setting up the problem. So we have this situation, right? What do we want to know? Calculate the distance, Caleb's starting point, Lauren's starting point. Sorry, guys. Calculate the distance from Caleb's starting point to Lauren's side of the creek. Round your answer to the nearest tenth. Okay, so we want Caleb's starting point to Lauren's side of the creek. So just here, not that whole distance, not to Lauren, just to Lauren's side of the creek. That's going to be our X. So we have similar triangles here because these are technically vertical angles, right? So they're congruent. And then we have the right angles, which are congruent. We have angle-angle similarity. So what we could then do is we could set up our proportion like we have been. So the distance they walk away is going to be the distance that just to set it up. So I'm going to say 50. We're going to take Caleb's distance over 12 over Lauren's distance. Those are the distances that they walked away from their starting point. Equals, and now we're going to do, in this little triangle that we have here, we're going to do Caleb, which is going to be the X, and then Lauren. And these are the distances from Lauren's side of the river, right? From the bank of the river. And now we just cross multiply. We get 50 times 5 will be, I want to say 250, but let me just double check. Always good to be safe. 50 times 5, yeah, 250. Equals, and we have 12 times x will be 12x. And we divide both sides by 12. And what do we get? On my right side, we're going to be left with x. On my left side, we do 250 divided by 12. we get 20.83 repeating. So we're just going to round it to 20.83. Oh, sorry. It says the nearest 10th. Good thing I read the directions. It says round your answer to the nearest 10th. That's the first decimal place. This is just going to be 20.8. So that is our answer. That is the distance from Caleb to that point right there. Awesome. So now it's saying, what is the width of the creek? Explain. So what do we know? What do we just learn? Let me color in what we learned. We learned all of that is 20.8. Right? That's what I said, right? 20.8? Yeah, 20.8. We know the 20.8. But we have this chunk here, and that's the distance from Caleb to the river. We have to take away from that. So we're going to say -5, which is going to give me 15.8. So we could say that the distance is 15.8, right? Because we learned the distance from Caleb to the other side of the river, but we have to take away the distance from Caleb to the shore. So what we did was we took the distance from Caleb to the other side of the river and subtracted the distance of Caleb to the shore, or right next to the river. That's what we ended up doing. Cool. That was an easy problem. And let's keep it moving. So it says there's also a ravine, and a ravine is a deep hollow in the earth, right? On another edge of the park, Rachel and Gavin take measurements to indirectly calculate the width of the ravine. The figure shows their measurements calculate the width of the ravine. So let's look at what we have going on here. So we have Rachel here, and they use the same situation. I'm assuming Rachel walks 15 feet down. We have Gavin here. Gavin walks 60 feet up. Because Rachel is 6 feet from the edge of the ravine, and then Gavin is 8 feet. But we also have a side of a triangle, which is from Gavin to the other side of the ravine, kind of like the last situation. That's what we want to figure out first. First, we're going to say that is X. That's from Gavin to the other side of the ravine. So let's set up our proportion. We're going to say the distance that Gavin walked, 60, over the distance that Rachel walked, 15, equals the distance from Gavin to our crisscross point here, go to the other side of the shore or the ravine, which is going to be X, over Rachel to that same point, which is going to be 6. So then, once again, what we do is we cross multiply. I'm going to do 15 times X, which will give me 15X equals 60 times 6, should give me 360. And then we divide by 15. Get rid of it. It cancels, and we're left with X equals. We get 360 divided by 15. And that's going to leave me with 24. But what does that 24 mean? That is this entire distance here. That's that whole thing. That's what that X is. Right? That's 24. We don't want to know that. We only want to know the width of the ravine. We have to get rid of this chunk here, which is 8. So what we're going to say is then 24 minus 8 equals, and that's going to give me 16. And there we go. We calculated the distance of our, or the width of our ravine. Great job. And these are real techniques that could actually work in person, right? It might be a little trickier. There might be a little human error measurement mistakes, but they would technically work the same exact way if you're able to do it. Which is pretty cool. Let's keep it moving. Just kidding. That's the end. So we went over a lot of word problems today, and it might be pretty confusing for some of you. I know word problems really ramp up the difficulty of the stuff we're learning. So as always, if you're stuck or if you're confused about any of the work that we just went over, make sure you ask the teacher that is your teacher, right? Or drop a comment down below. As I always say, I'll get back to you the best of my ability, right? So I hope you guys had a understanding of a lesson, and talk to you next time. Peace.